All right, we have our next one. What we have is an old style garage door. So here's the garage door. It's 8 feet in length. We're going to treat that as a slender rod. And in the old doors, what you'd had is you had these two tracks. And so what happened is, so here you have these pins. So initially the door is up here. When you open the door, you actually had, as this pin goes out and this pin goes up here, when the door was open, it actually protruded out some. So for this problem, it would protrude out 3 feet. Now that would, in the old days, that was actually perhaps a tad useful because garages tended to be really small, not very deep. So the idea is you could actually pull something into your garage and be taking things out of the back, and you had protection from the elements with the door there behind you up in the air. All right. When you wanted to put the door down, then this pin slid down that track, this pin slid over, and you'd have the door just vertical and closed. All right. So it's 8 feet long. Here's the pin at B. So G, for an 8-foot door, there's 3 feet of overhang here. So B to G is 1 foot, and then G to A is 4 feet. All right, in the logical way. Door weighs 180 pounds. All right. And so here's what we're given. The door was up, and it's released from rest. And we don't have any springs or anything helping keep it up, so we don't have to worry about that. So this, when the door is up, that angle theta would be 0 degrees. And so the problem says when the door gets to 30 degrees, which is nominally what, this isn't perfectly to scale, but that's nominally what's shown here. So picture theta at 30 degrees. Find omega of the door. So we have displacement, we have velocity, we have an energy problem. All right. So we're going to go to, let's keep that down here. So for energy, we're starting here from rest with this door vertical. So T1 is 0. I'll take when the door is up high as my 0 reference. So V1 becomes 0. So we have 0 equals T2 plus V2. So what's happening here is the door comes down, it gives up potential energy, it goes into the kinetic energy. Makes sense. All right. So next step. Let's look at T2. And so let's see what we're going to have. This door is going through some complex motion. It both has translation and rotation. All right. If it was pure rotation, when it was up, it would just rotate down like this. But no, it's translating and rotating to get there. So that would say we're going to have two terms: 1/2 mv squared, so there's Vg, and 1/2 going at G, Ig omega squared. We're not in pure rotation, so I need both terms. This is a slender rod, so that would correspond, if you looked at the table, to Ig would be 1/12 ml squared. We've seen that before. So here we have 180 on 32.2, length 8 feet squared. So there's all that, 1/2 I omega squared. So to solve this problem, now it's very easy, since this is 4 feet, we'll just look at V2, 180 pounds. How far has it dropped? 4 sine 30. So V2 is easy. So when we solve this problem, 0 equals this plus that. So doing this part of the problem at this point shouldn't be a challenge. The problem is we need to have an equation relating omega and Vg. That is a challenge. You have to think about how we're going to approach that, because I need one variable to solve this equation. Where are we going to get that? Well, we're going to get it from a very interesting source. Now keep in mind, I talked about on your exam, the exam would not focus on, say, instant centers, but it could have instant centers as a component of what's going on. Often in these problems, you need an extra equation. Kinematics, instant centers, those are all tools for getting that extra equation. And this is the case here. I'm going to use instant centers. It's a really easy approach. So what I need to get is for when the second state, so when the door is in this position, I need to know an instant center. Why? Let's say this point where I put my finger is the instant center. So this would be a point of 0 velocity. Then Vg would be omega times this r. And so then I could replace Vg with omega times omega times r, or I can come in here and put Vg over r, whichever one I wanted, squaring them. All right, so an instant center will allow me to do that. So how do we get an instant center? Well, we'll notice the velocity at A is going in the usual negative x direction. The velocity at B is going in the usual negative y direction. And where is the instant center? Given two velocity directions perpendicular to each of them. So if we came down here and over from there, it would be right basically where my finger is. And then we could just measure what this r is from this instant center to G. We'd have r, bam, we'd be done. All right. My finger's not good enough. We need to use a little more effort. So that's what I have here. So we've just talked about, to get our equation to solve our problem, we're going to use instant centers. So knowing VA goes this way, I drop a vertical here. Knowing B is dropping, I run a vertical over here. So that's the instant center. And so I can use simple trigonometry. So I know it's 4 foot to G, 1 foot to B. We had 5 feet. Let's just come down here. From A to B was 5 feet. G's 1 foot over because it's an 8-foot door. All right. Take note of that. So we're going to lose this here in a moment. Let's see. Can we keep it all? Actually, we can. All right. So I have 5 feet. Cos 30 gives me 4.3301. Sine of 30 is a half. So knowing that here's 5 feet times sine of 30.5, here's 2.5 right here. So this is 4.3301, and obviously 2.5 going up. What I need now is this distance from here to there. And so I'm going to use the law of cosines, one of the tools that you should have had from any number of places, one of which was Eng 1082. All right. So if this is 30, we know from geometry that this angle in here is 30. So I'm going to use the law of cosines. The law of cosines basically says this: distance squared is equal to that squared plus that squared. For this triangle, it's this piece, that piece. This distance squared is this squared plus that squared minus 2 times that, and then times the cosine of the angle between them. If you need any help, go check your geometry text from the past. Check Eng 1082. You can go online and find all sorts of stuff about the law of cosines. It's a tool. The law of cosines, the law of sines are tools you need to have in your back pocket to use on a whim. It's expected. All right. So here's this equation. So we solve for that. We get D is 3.5 feet. Well, then VG is 3.5 times omega. Sticking that up into here. And so there's that result. D is 3.5 doing the law of cosines. This gives us this equation. Sticking that up into the top, we can solve, and we get omega is 2.71 radians per second. And it's obviously going counterclockwise as this thing rotates like that. 2 more problems to do, and we're done with energy.